Good morning, my dear students. Our lecture today is about the solution of the wave equation using the method of separation of variables. So at the beginning, we start by stating the problem. We are given this wave equation, partial square u by partial t square equal c square, partial square u by partial x square for x in the interval from 0 to L and t is bigger than 0. So associated with this differential equation, two initial conditions. The first initial condition, u of x0 equal f of x for x in 0 and L, and partial u by partial t of x and 0 equal g of x for x in 0 and L. We have also homogeneous Dirichlet boundary conditions, this condition in equation 4. And our lecture aim is to derive a solution for this wave equation based on the method of separation of variables. The method of separation of variables suggests that the solution function u of x and t is composed as a product of two functions. One of them is a function in x, the other function is a function in t. Neither of these two functions shall be zero, the zero function, because if any is the zero function, it will lead to the trivial solution u of x and t equals 0, which is rejected. So now from this equation, I mean equation 5, in which we separated the variable x from the variable t, when we look at the second derivative of u with respect to t, we see that x will deal with the function x of x will deal with as a constant. So when we compute the second partial derivative of u with respect to t, this is a constant, and then we here we compute the full second derivative of t with respect to t, and that gives x of x times t double dot of t. The same for the second partial derivative of u with respect to x, where t of t is considered a constant, and then the second partial derivative of u with respect to x becomes the second full derivative of x multiplied by t of t. If these forms of the second partial derivatives of u with respect to t and with respect to x are substituted in the wave equation, we will obtain this equation here, x of x times t double dot of t, which is written instead of partial square u by partial t square, equals c square times x double prime of x times t of t, which is written, I mean, in place of the second partial derivative of u with respect to x. So let us see what happens to the boundary conditions. The first boundary condition says u of 0 and t equals 0. So when we substitute x by 0 in this expression here, we obtain x of 0 times t of t, which is written here, and we equate it to 0. From the beginning, we assume that t of t is not 0, so that leads to x equal 0. The same for the second boundary condition when x is substituted x equal L here. then u of L and t is x of L times t of t, which is this part here. And since u of L and t is 0, then that and t of t is not 0, then that will lead us to x of L equal 0. If we divide equation 6 by c squared times x of x times t of t, we will obtain the two terms in equation 7 here. That is t double dot of t over c squared t of t equal x double prime of x over x of x. And the important notice here in equation 7 is that at the left hand side we have a function in t. At the right hand side we have a function in x, and we are requiring them to be equal. And actually this can never happen unless both the two terms is a constant. So we suppose that the two terms are constants and they are equal to some constant lambda, where lambda is some real number. Now if we take the second and the third terms here, we will obtain the ordinary differential equation x double prime of x minus lambda x of x equals 0. And if we consider the first term with the third term, we obtain from it another ordinary differential equation t double dot minus c squared lambda t equal 0. And that means the method of separation of variables transforms the wave equation into two ODEs. And actually here we have like three cases for the parameter lambda. Lambda could be bigger than 0, or it can be 0 or less than 0. So in the next slides we are going to discuss these three cases. The first case is when lambda is positive, and in this case we can write lambda as a square of some number omega. And when we substitute that in the differential equation, we will obtain this boundary value problem, x double prime of x minus omega square x equals 0, with the boundary conditions x of 0 equal x of L equal 0. And the solution for this differential equation is a linear combination of the sine and cos functions. So we can express it as C1 cos omega x plus C2 sine omega x. Now we substitute the boundary conditions to compute the values of the constants C1 and C2. So if we substitute the first boundary condition, x equals 0, we will have C1 times cos omega 0 plus C2 times sine omega 0 equals 0. We know that sine 0 is 0, so that, and cos 0 is 1, so that leads us to C1 equal 0. That means x of x is C2 times sine omega x. Now we substitute the second boundary condition. That means we substitute x equal L, and from it we obtain C2 sine omega L equal 0. But since L is strictly bigger than 0, sine omega L is not 0. Okay, it is a positive value, that is not 0. And that means C2 is 0. Okay, so that leads us to, if C1 and C2 are both zeros, then that will lead us to the solution x of x equals 0, the trivial solution, which is rejected. Let us see what will happen when we consider the second case when lambda equal to 0. And in this case, our differential equation x double prime of x minus lambda x equal 0 becomes just reduces to this equation. The second derivative of x is 0, together with the boundary conditions x of 0 and x of L are zeros. So the solution of this differential equation is obtained by integrating twice, okay? And then we obtain the solution x of x equals c1 x plus c2. And when we substitute the first boundary condition x of 0 equals 0, then that means here we substitute x by 0. So this term vanishes, and then we get from it c2 equal 0. That means x of x is in the shape of c1 times x. Now we substitute the second boundary condition in L. So x of L equals 0. It means that c1 L equals 0. And since L is not 0, then c1 is 0. And this leads again to the trivial solution, which is again a rejected solution. Okay. The last case is that lambda is less than 0. That means lambda is a negative value. So we can express lambda as negative omega square for some real number omega. And then our differential equation x double prime minus lambda x equals 0, it becomes x double prime plus omega square x equals 0, together with the boundary conditions x of 0 equal x of L equal 0. Now the solution of this differential equation from the first course is written in terms of the sine and cosine, because the two linearly independent solutions are the sine and cosine functions. So we write x of x equals c1 cosine omega x plus c2 sine omega x. We substitute the first boundary condition x of 0 equals 0. So here we obtain c1 cosine omega times 0 plus c2 sine omega times 0. This is 0, this term is 0. Cosine omega 0 is, which is cosine 0, that is 1. 1 times c1 is c1. So that gives us c1 equal 0. Okay? And that means we this x of x is just c2 times c sine omega x. Now we substitute the second boundary condition in L. So x of L equals 0. That means c2 sine omega L equals 0. And in this time, because now we do not have any more options, c2 must not be 0. So sine omega L can be 0 when omega L is a multiple, I mean is integer multiple of pi. So if omega L equal n pi, then sine omega L is 0. And from this, we know that omega is n pi over L. By dividing the two sides by L, we obtain omega equal n pi over L for n equal 1, 2, and so on. Now our solution x of x will be c2 sine n pi over L x for x in 0 and L. And yes, we actually accept this solution. And because x, I mean there are infinite number of functions that are satisfying the differential equation and its boundary conditions. we just write xn of x. I mean, these solutions can be obtained by changing the values of n from 1, 2, and so on. We write xn of x equals cn sine n pi over L x. We solve the second ODE in T, which we read T double dot minus lambda T lambda Ct equals 0. It takes this value after we substitute lambda by its value minus omega square, which is minus n square pi square over L square. Then we obtain this differential equation. And when we solve this differential equation, the solution is again in terms of cosine and cosine functions. So we write Tn of T equal An cosine Cn pi over Lt plus Bn sine Cn pi over Lt. And we have characterized the solution again by n, because for different values of n, we can find solutions that are satisfying both the first boundary value problem and this ordinary differential equation. So now we write Un of x and t equal xn of x times tn of t, which is this amount here, and for n equal 1, 2, and so on. Okay. That means we have infinite number of solutions that are obtained by substituting the different values of n. Now these functions Un of x and t are called the eigenfunctions of the vibrating string, and the values of the lambda n corresponding lambda n's are called the eigenvalues, or also may be called spectrum. Now we use the superposition principle to express the solution function u of x and t as a linear combination of the eigenfunctions Un of x and t. So that means u of x and t equal summation Un of x and t from n equal 1 to infinity, and then at this side we just replaced Un of x and t by its formula. What is remaining is to determine the constants An and Bn in this form of the function of x and t. So now we are going to use the initial conditions to find these constants here, An and Bn. When we substitute the first initial condition, u of x and 0 equal f of x equal, now when we substitute 0 instead of t here, we obtain cosine 0, which is 1. So we obtain An from this term here. And sine 0 is 0, so this term cancels. And then we remain with summation An sine n pi over L x. From the Fourier series, okay, we know that An is just 2 over L times the integration of f of x sine n pi over Lx dx from 0 to L. So we can compute An from the Fourier series. When we differentiate u with respect to t, actually we can obtain this derivative here inside the sum, because this is constant with respect to t. So we just differentiate the first and second term. So the derivative of the cosine is negative sine, and then we multiply by the derivative of the inside function, which gives this coefficient here. And the derivative of the sine is positive cosine multiplied by the derivative of the inside, which gives this constant value here. Now, when we substitute the second initial condition, t equals 0 in the derivative, we obtain the second initial condition, g of x equal this summation. Now here we see that the first term, we have sine 0, which is 0, so this term cancels. From this term, cosine 0 is 1, so what we get is cn pi over lbn times sine n pi over lx, equal dx, the summation. And from the Fourier series, we know that bn will be 2 over L multiplied by the L over Cn pi. And it gives us this formula for Bn. Finally, we conclude the Fourier solution of the wave equation as follows. The function, solution function u of x and t is written as the summation of an cosine cn pi over lt plus bn sine cn pi over lt times sine n pi over lx, where an is 2 over l times integration f of x sine n pi over lx dx from 0 to l, and bn is given by 2 over cn pi by the integration from 0 to l of g of x sine n pi over lx dx. We consider this example to show how the method of separation of variables works. So we read the example. Solve the wave equation 1 to 5 for g of x equals 0. And here we have two cases for f of x. The first form of f of x is sine pi x over l plus quarta sine 3 pi x over l. The second form is f of x equal x for x between 0 and l over 2, and l minus x for x between l over 2 and l. Now for solving the problem in the first case, first we notice that since g of x is 0, then that will lead us directly to bn equal to 0. That means we left only with the form ux of t equals summation an cosine cn pi over lt times sine n pi over lx. That means our problem is just to find the value of the constant an, constants an. Now from the Fourier series, the an is given by this form here. Now we substitute f of x by the first case, okay, and we obtain this value. The an is 1 for n equal 1, half for n equal 3, and it is 0 otherwise. That means we have only the two cases when n equal 1 and n equal 3. So if we substitute n equal 1 here in this term here, a1 is just 1 cosine c pi over lt sine pi x over l, which is the first term written here. When we substitute n equal 3, we have a3 is half, we write it here, cosine 3c pi t over l, which is this term here, sine 3 pi x over l, which is this part here, and then it is 0 otherwise, so that means what we have here is the solution of the wave equation. Now for the second case, again we have bn equal 0, because g of x equal 0, and still the solution is u of x and t is summation an cosine cn pi over lt times sine n pi over lx. Now we evaluate En using the Fourier series from the Fourier series. So En is 2 over L times integration from 0 to L f of x sine n pi x over L dx. We can divide the integration from 0 to L as express it as a sum of two integrals, one from 0 to L over 2 and the second from L over 2 to L. And when we compute this integral, we obtain this form: 4L over n square pi square sine n pi over 2. Now that means we are going to substitute this formula instead of An here. So that means u of x and t equal, actually the 4L over pi square is a constant, so we can take it outside the summation. And what we obtain inside the summation is sine n pi over 2 over n square, written here, and then the rest, which is cosine cn pi over lt times sine n pi over lx. Thank you for attending this lecture, and I'm hopeful to see you in the next lecture, which will be about the D'Alembert solution of the wave equation. Thank you and see you.